Hey everyone, my name's Noah. These are my group mates Aiden and Curtis, and today we'll be giving you a quick presentation on our biomass-derived carbon electrodes.
So our focus for this project is on carbon electrodes that would be used in flexible supercapacitors. So with the demand for wearable electronic devices such as Apple Watches and Fitbits increasing, many companies are now investigating new flexible electrode material. So currently carbon materials are being used in the forms of carbon nanotubes or graphene oxide, but both of these come with high production costs and are potentially hazardous to the environment. Whereas lignocellulosic biomass is naturally abundant, low cost, and has excellent electrochemical stability, which makes it a great alternative for manufacturing these flexible electrodes, and will be the material that we'll be focusing on in this report. So just a little background on supercapacitors before we start. A supercapacitor is a device used for energy storage. It does this by creating a double electrostatic field between two plates when connected to a power supply. So why they're used over batteries is because of their higher power density, which gives them faster charging and discharging capabilities. And why they're used over regular capacitors is because of their higher energy density, which allows them to store more energy. So they're basically an in-between of a battery and a regular capacitor. And in general terms, it can be thought of as a electrical equivalent to a flywheel in a machine.
So the process from going from a biomass such as the lignin and other food waste products to the actual supercapacitor is you first have to collect all the biomass such as lignin, shells, husks, peels, and whatever. And then it undergoes a process called pyrolysis or carbonization. So the process of is where biomass is cooked and converted into a carbon state char. This is done by heating the biomass in an oxygen-free / limited space, and it's cooked around 600 degrees Celsius for an extended period of time until you get a biochar. Then we are left with a highly microporous activated carbon, which is then used to make the super electrodes.
So the properties of these carbon electrodes are good conductivity and electrochemical stability, as well as high specific surface area. These are all what gives it its good capacitor performance. They're also lightweight and flexible, which allows them to maintain stable electrochemical performance during periods of deformations, such as folding or stretching, or in this case, wrapping around a wrist. And the material is extremely low cost due to its natural abundance and will be very sustainable in the long term.
As for the environmental impacts, these supercapacitors pose no major threat to the environment as they're environmentally friendly and the biodegradable materials are used to reduce the environmental impact. So a life cycle analysis, or LCA, of the activated carbon, AC, from coconut shells actually showed that the use of these renewable resources from the production of AC would reduce both the human toxicity and global warming, which is great. And for these things, they actually supply about 14% of the world's energy due to them being, like Curtis said, readily available, low cost, and they regenerate rapidly, and they're very environmentally friendly when compared with fossil fuels. As for the economics, although this kind of material offers large volume and are environmentally friendly, they do suffer from very low carbon yield during the activated carbon production, leading to poor economics. The cradle to gate life cycle analysis study of the activated carbon from woody biomass showed that the cumulative energy demand would potentially decrease by 35% compared to coal-based activated carbon. As for the costs of this kind of material, from pecan shells, at least in a plant with a 10,000 kilogram capacity per day, was estimated to be about $2.89 US dollars per kilogram. But as for the lignocellulosic material, no major assessment of the economic feasibility has been done at this point. So we were kind of limited with our research. Here is our references, and I appreciate everyone for taking the time to listen to our presentation today.